So, then in this module I am going to talk about more results. So, let me just introduce another result in the name of another theorem. I am calling it theorem 4. It tells me that if I have Fourier transform of small f denoted by capital F at k and Fourier transform of small g denoted by capital G of k, then the result tells me, this theorem tells me that the Fourier transform of the convolution of the two function is the product of the Fourier transform, the product of the Fourier transform, or it is equal to f of k times g of k, right. So, the Fourier transform of the convolution is quite easy to calculate, which is given by the product of the Fourier transform. Now, this is something that I would ask the students to check. Okay. So, this is quite easy to check. You define, we already know what is for the convolution of two function, then you have to figure out, you have to apply the Fourier transform of that convolution function by use the standard definition, and from there you have to separate out the two integrals, one corresponding to the Fourier transform of f, the other corresponding to the Fourier transform of g, to arrive at this result. Okay. Now, then there are some corresponding corollaries or side results. Let me talk about it as 4a. So, these are some of the properties of convolution, right. So, in particular one of the properties says that f star g is g star f. So, it does not matter about the order of convolution. Then another property is that f star h star h, sorry, f star g star h is f star g star h. So, what this property tells us is that it does not matter about the order of convolution. So, you can either take this convolution first or this convolution first. So, the answer will be the same. Then convolution is a linear operator, right. So, in particular I have alpha f plus beta g convolved with h is alpha of f star h plus beta of f star g. So, it is a linear operator. And finally, another important result is that the convolution of the delta function is the delta function. So, the delta function also obeys our corollary 4a. I introduced this last result separately because delta function is not a function in the classical sense, as I outlined it in my earlier lecture. Okay. So, then I have one more result which I am going to introduce in the form of another theorem called the Parseval's relation. Parseval's relation. So, what is Parseval's relation? Well, Parseval's relations are quite useful when we have to take the inner product of two functions, or suppose we were to define the Fourier transform of the product of two functions, then Parseval's relations are quite useful in those sort of evaluations. So, let us see what is this Parseval's relation. So, if I have again f of k and g of k as my Fourier transform of f and my Fourier transform of g, then the relation tells me that integral from minus infinity to infinity f of x times g of x conjugate dx is the same integral in the Fourier transform f of k g of capital G of k conjugate dk. Okay. So, these are your physical functions, these are your transformed functions. Okay. So, let me show you the proof quickly, because this is quite an important result. So, I am going to start with my right hand side RHS. So, my RHS is from negative infinity to infinity f of k g k absolute value d k, right. Now, I am going to use my definition of Fourier transform. This is also equal to integral from minus infinity to infinity d k, right, and then each of these are Fourier transforms. So, that will bring in a factor of square root 2 pi. So, that will be squared, I get 1 by 2 pi, right. So, integral from negative infinity to infinity e to the power I k y f of y dy, and then integral. So, this is multiplied by this integral from negative infinity to infinity e to the power I k x g x dx, and then I take a conjugate of it. Okay. So, then when I do that, I get 1 by 2 pi integral from minus infinity to infinity f of y dy. So, I have interchanged my integration variable here. So, integral from minus infinity to infinity g x dx with the conjugate, right, and then I have another integral, that is the k integral from minus infinity to infinity e to the power I k x minus y dk, right. Okay. Now, I want to highlight that this particular function, this particular integral, this was done earlier, that this is nothing but the delta function. Okay. So, what I get is as follows. So, this becomes well this function and this function, right. So, what I am trying to show here is that my delta function x minus y is 1 by 2 pi integral e to the power I k x minus y dk. Okay. So, that is what I have used here. So, then I get the following integral from minus infinity to infinity g bar x dx. So, I keep interchanging my variables of integration just to show you conveniently. Integral from negative infinity to infinity f of y delta x minus y dy, right, and then what I get is the following. I get negative infinity to infinity. Now, this integral in the interior, since this is multiplied with a delta function, I am going to get just one value, that is f evaluated at x. So, finally, I am left with the following result. This is g bar x f of x dx, and that is my left hand side of my Parseval's relation here. Okay. So, you see that the inner product or the inner product of the two functions in the physical plane is the inner product of the two function in the transformed plane, right, and they are equal. Okay, then I am going to introduce a popular application, popular application of Fourier transform, namely the Shannon sampling theorem. Okay, so before I move on to describe what is this Shannon sampling theorem, I just want to highlight that this theorem, this particular result is a very important bridge between connecting continuous functions and discontinuous or discrete functions. Especially in the area of signal processing and communication, Shannon functions or Shannon sampling theorem plays a major result, which helps us to connect discrete signals into time continuous signals. So, let us see what is this Shannon transform or Shannon sampling theorem. So, as I said, in digital signaling, in digital signal processing, so I am just going to build up some useful terms here. So, in digital signal processing, I have an analog signal. I have an analog signal which is denoted by Ft. So, this is my analog signal Ft, right. So, Ft is a continuous function of, let us say my variable is time t, and t I am going to take, well, I am going to take without loss of generality from negative infinity to infinity, right. You will see why this choice is taken. So, it may seem to be a bit counterintuitive to take this limit for the time t. Okay. So, I have, so Ft is an analog function which is a continuous function such that I have Ft, I need this Ft to be L2 integrable from minus infinity to infinity, right. So, which means when I say Ft is L2 integrable, I say what I mean by that is that the norm of f is given by this following integration from negative infinity to infinity, we take the square root. Okay. Typically in physical application, this norm, this particular norm denotes the so called energy content, right. So, what do I mean by that? So, suppose you have wide spectrum. So, suppose you are trying to represent your information with this analog signal, right, and we want to see how much energy or how much, what is the amplitude of this signal for all such possible frequencies k. So, what we do is we find the norm of these function, and that gives us the total energy content of the signals that are being transferred. Okay. So, that is what I mean by this energy content. So, it could be either in well, real or the frequency domain, right. Well, why? Because they are the same in the real and the frequency domain because of our Parseval result, the Parseval theorem that we had proved earlier. Now, let me introduce another definition. So, my signal Ft is band limited. I introduce this notion of band limited. It is band limited if its Fourier transform is given by this function f a of omega, where f a of omega is defined to be 0 for all frequencies which are bigger than some cutoff frequency a. So, I call this a as my cutoff frequency. So, you can see that if the signal is band limited, then it is non-zero only for a particular range of frequency. Outside that range, the frequency will be, the signal will be 0. Okay. Then the corresponding signal is the band limited signal is denoted by f a of t, right. So, I call this as my band limited signal if my Fourier transform is 0 outside a particular cutoff frequency. So, in general I can always reduce. So, Ft, if Ft is not band limited, I can always reduce Ft to a band limited signal. How? Notice. So, Ft can always be reduced to a band limited signal by the so called low pass filter. Filtering. So, again, what is low pass filter? That is another function, right. So, what is this function? So, if I have an analog signal f, right. So, this is my analog signal which is a time continuous function, and we want to reduce it into a band limited signal. We want to reduce this, right. So, I am going to introduce, for that I am going to introduce my band, I am going to introduce my Fourier transformed function f a of omega, which is your usual Fourier transform inside this range of frequency and 0 otherwise. Okay. So, what I am trying to do is, if I have an analog signal and I want to reduce it to a band limited signal, I introduce its Fourier transform such that it is 0 outside a particular domain. So, then of course, when we take an inverse transform, I get that the signal is the band limited signal. Okay. So, then what is the band limited signal? The band limited signal is given by 1 by 2 pi integral from minus a to a e to the power I omega t f of a d omega, right. So, this is my inverse transform. This is my inverse transform of f of omega, right. Now, notice that I have used a factor of 2 pi, not 1 by 2 pi square, 1 by 2 pi, not 1 by 2 pi square root. So, the fact is that we are using the definition used by the electrical engineers that was introduced in my lecture 1, right. So, I am introducing angular frequency instead of my wave number. So, that is another definition of the Fourier inverse and the Fourier transforms. Okay. So, for this band limited signal defined by this result, this is also called as my Shannon sampling function. Shannon sampling function. Okay. So, if I have that my a is pi in that particular case, so that is a particular case, then I have the Shannon scaling function. Shannon scaling function. Okay. So, f is my Shannon sampling function. So, I am going to use this result to show what is my Shannon theorem. Okay. So, then so again, so I have my band limited signal. So, this is my band limited signal, f t of a defined as 1 by 2 pi integral minus infinity to infinity, right, and this is equal to, earlier it was from, let me just introduce the correct notation here. It is from minus a to plus a f a of omega e to the power I omega d omega. Now, let me just replace this by the infinite integral. This is 1 by 2 pi from minus infinity to infinity integral f of omega e to the power I omega d omega, right. I know that f of omega is 0 if omega is outside this cutoff range, right. Okay. So, then let me further take the fact that this f of omega is 1 if we are inside the cutoff range, right. So, I call this as my gate function, So, in a gate function, the Fourier transform functions are specifically defined inside the cutoff range and outside the cutoff range. So, in that case I get that this is also equal to 1 by 2 pi from minus a to a e to the power I omega d omega, and this integral can be readily evaluated to see that this is equal to sin a t divided by pi t. Okay. So, I get that for a gate function my band limited signal is given by this following closed form expression sin a t by pi t. Okay. So, conversely, if I have look at the Fourier transform of this constant 1. So, the Fourier transform of 1 is given by limit integral from minus infinity to infinity e to the power I omega t f of a t dt, right. Because the way we have described this band limited signal, it is described in terms of the gate function, right. So, 1 is given by this following Fourier transform. Notice that the 1 by 2 pi square root is absent here, because the way we have described the Fourier transform in this frequency domain. Okay, then we are going to take the limit of this integral for a going to infinity. So, we are going to take the limit in this function, we are going to take the limit a going to infinity. So, notice what happens. So, this is equal to integral from minus infinity to infinity e to the power negative I omega t, and I take the limit inside limit a going to infinity. That can be done for continuously differentiable functions. So, this becomes, I replace my f of t, f a of t by sin a t by pi t, right, and then this is dt. Now, what I have is the following. So, this is nothing but delta function. This is another definition of delta function. Okay. So, specifically, so we have another definition of delta function given by limit a going to infinity sin a t by t, right. If it is not intuitively clear, you students should plot this function and allow this parameter a to go to infinity and see that it approaches delta function, right. So, then coming back, I have 1 is equal to, so this is also what the above is also another definition quite commonly used for delta function. So, then I have 1 is given by integral from minus infinity to infinity e to the power I omega t delta of t dt, right. And so, what I am left with is that, well, so we have the following result, which brings us to this definition as well, right. Okay. So, then I have the following. So, let me continue. So, I have the band limited signal f a of t. So, I am just processing my result again and again to arrive to a certain result. So, my band limited signal f a of t is 1 by 2 pi integral from minus a to a. It is the times the gate function e to the power I omega t d omega, and then of course, this is also equal to 1 by 2 pi from minus infinity to infinity f omega f a omega e to the power I omega t d omega, right. So, we see that this is nothing but the Fourier transform inverse of the product of two transform functions f omega times f a of omega, right. So, this is the Fourier inverse of the product of two transforms, this particular integral, and I get that. So, using the result that the product of two Fourier transform is the convolution of the corresponding function, I get that this is also equal to the convolution of f with f a t minus tau d tau, right. and then of course I can replace this by my known result for f a. So, this is integral from minus infinity to infinity f of tau sin a of t minus tau divided by pi t minus tau, right, and d tau. Okay. So, what I have done is I have represented the band limited signal, in terms of the convolution of these two functions, the convolution of sine of a t by pi t. So, this is the convolution. So, my band limited signal is a convolution of your original signal with this factor, right. So, I call this result, I call this representation as my Shannon integral representation. Okay. Okay, so, I am going to end this module and continue to the next module describing what is this Shannon integral representation and how does it connect with our Shannon sampling theorem. So, let us consider the Fourier transform of the band limited signal. F a of t, right. So, then I know that this is also equal to my f omega, which is 0 if outside the cutoff frequency and of course non-zero when inside the cutoff frequency, right. So, that is my band, the Fourier transform of my band limited signal. So, I can always write my Fourier transform in terms of this series, in terms of this orthogonal sets from n from negative infinity to infinity a n e to the power negative I n pi by a omega, right. So, I know that these are my orthogonal sets, right. So, these are my orthogonal basis functions or the Fourier basis. I call this as my Fourier basis, right. So, I can always represent my Fourier transform in terms of this relation, and of course, my Fourier coefficients a n is given by 1 by 2 a. I am taking the inner product. So, since the fact that these are orthogonal basis function, I am taking the inner product to find a n's, right. So, 1 by 2 a f omega e to the power I n pi by a omega, right, d omega. Now, notice that this is nothing but 1 by 2 a times the band limited signal evaluated at n pi by a, right. So, if I replace this by t, then I get that this integral is equal to f a of t. So, this is, so the coefficients are 1 by 2 a f a evaluated at this argument. So, I am going to use this result. So, my f omega, the Fourier transform is 1 by 2 a summation n from minus infinity to infinity a n is 1 by 2 a times f a at n pi by a e to the power negative I n pi by a omega. So, I have just used this relation here. Okay. So, what I see is, let us just keep looking at this expression. What I have is that this is also equal to, so my f a, finally the band limited signal f a is 1 by 2 a integral from minus a to a f omega e to the power I omega d omega. That is the basic definition coming out of the inverse transform. Now, this is also equal to 1 by 2 a integral from minus a to a e to the power I omega t d omega, and I am going to replace this by this result above. So, this thing is going to be replaced by this thing above, right. So, let me do that. So, again f a of t is 1 by 2 a integral from minus a to a e to the power I omega t d omega summation n from minus infinity to infinity f a n pi by a. So, I am replacing my expression for the Fourier transform of the signal f omega, capital F omega, e to the power negative I n pi omega by a. Okay. So, then I get this is also equal to 1 by 2 a summation n from negative infinity to infinity f a n pi by a. So, I have taken this sum outside and the integral inside from negative a to a e to the power. Notice how I am combining this exponential with this exponential I omega t minus n pi by a d omega. Okay. So, then we see that this integral, this particular integral along with this factor will provide us with the following result. So, this becomes n from negative infinity to infinity f a n pi by a times sin a t minus n pi by a divided by divided by a times t minus n pi by a. Okay. So, what I am getting is that f a, the band, this is a continuous function, this is a continuous signal, and these are discrete sums, right. So, this is the result that I was trying to arrive at, also known as the Shannon sampling theorem, and what it says is that I can represent my continuous function by an infinite sum of discrete functions, or if I have some discrete signals, I can construct my continuous signal by the following summation of the discrete signals. That is the power of this theorem, the Shannon sampling theorem. So, specifically it tells us that any band limited, so let me write down the statement of this theorem. So, any band limited continuous signal of, let us say, bandwidth a can be reconstructed from infinite set of discrete samples, infinite set of discrete samples of f a at 0 at all these points, integral multiples of pi by a, right. So, this is what the result shows us. So, you can construct a continuous signal out of the infinite sum of discrete signal, and that is what the theorem says. Okay. So, I want to end this discussion by providing few more topics of interesting topics of interesting reading, right. So, people who are specially working in this area of low pass filtering, band pass filtering or Shannon sampling theorem, they should also look at topics like transfer functions, what are these, right, impulse response functions. So, these interestingly, all these ideas, all these notions could be very easily described by our Fourier transform theory that we have just developed. So, low pass or high pass filters, or we have resolution of signals and so on. So, these things are quite interesting to read in this area of application.